Welcome to the video, How to Use Python to Compute and Sketch the Magnetic Field of a Current Loop. I am Ronald Johns. We're going to be using the Biot Savart law, dH equals 1 over 4 pi dl cross r hat over r squared, where h is called the magnetic field intensity. It is a vector field. What we want to do is something like we see in this illustration over here. We have a circular loop of current, and it's symmetric about the origin, and it's in the xy plane. And we want to compute the vector field, which is shown by these arrows out here, by using the Biot Savart law. Our goals for this video are to understand the Biot Savart law, how to compute H, the H field produced by current flowing through a wire, differential piece by piece, and also to use Python to compute and sketch the three-dimensional H field for a current running through a circular loop. The circle will be in the xy plane, and it will have radius 2 and center at the origin. We're looking at a three-dimensional problem here, the H field in a three-dimensional region around that loop of current, but the circle itself, the circular loop of current, will be in the xy plane. This is the sort of graphic that we want to produce using Python. This is a rendering of a three-dimensional vector field with a red loop of current down here in the xy plane. This figure can be rotated around so that we can get various views of what is going on. Let's talk about the Biot Savart law. Basically, we are going to have a differential version of this law, which is shown right here. Here's what's happening. We have a little chunk of wire of length dl, a differential, and we have a current I going through this piece of wire, and we'll assume that I is a constant with respect to time, and somewhere out in space we have a point P. This is three-dimensional space. Let's let r be the distance out to this point P, and let r hat be the, r will be a vector, and let r hat be a unit vector in the same direction as r. In that case, for the H field, magnetic intensity, we have that the bit of the H field contributed at this point by this current going through this wire is going to be called dH, and it's 1 over 4 pi dl cross r hat divided by r squared. So basically we have, I guess you can say, an inverse square law here, since we have an r squared in this denominator. And then if we look at just very small pieces that are not necessarily differentials, if we think of this as the kth little piece of wire, and we want to know the contribution to the H field just from that piece, we would have delta H sub k is equal to 1 over 4 pi, I over 4 pi, delta L sub k cross product with r sub k hat divided by r sub k squared. And if we let r sub p be the point with coordinates x sub p, y sub p, z sub p, that's going to be this vector here, basically, going from the differential wire element out to the point P in space. Let those be the coordinates of a chosen point in P in space, and we want to calculate the value of H at r sub p, and we'll call that H of P. we'll go from the differential viewpoint to a macroscopic viewpoint. We could have, for instance, a loop of wire here, circular loop in the XY plane, and we could have a point P out here in space, and we would like to know what magnetic field, magnetic intensity field we have at P due to a constant current I flowing through this circular loop. Well, we need an equation for the circular loop. Here's a parametric equation for it. Let C stand for circle. R sub C of theta is A, the radius here, whatever that is, times the vector cosine theta, sine theta, 0, where theta is between 0 and 2 pi. So that's going to be the position function for points on this circular loop. Different values of theta will give you different points on this circular loop. And as I mentioned before, we'll let a constant current I flow through that circular loop. Here I'm going to let A equal 2 in this formula, A times this vector, so that this circular loop is going to be centered at the origin, it's going to be embedded in the XY plane, and it has radius A. So in our Python program, we will change from a continuous model to a discrete model, and we will use numerical integration, actually just Riemann sums, the simplest form of numerical approximation to an integral, for our computation of the integral of a vector-valued function. Our numerical integral, as I mentioned, is going to be Riemann sum, and I should mention that there are many methods of approximating these integrals which are covered in numerical analysis courses. Some of them require quite a bit of theory to get a formula for, but they might give much more accurate results. In our case, we're going to use pretty small subintervals in our Riemann sums, and our results will be quite accurate. To solve our problem, one of the ideas we will use comes from Calculus 1. Suppose we start with a smooth curve. It could be quite a long curve, going up, going down, and so forth. But as you zoom in on a smaller and smaller piece of that piece of the curve becomes straighter, more and more like a straight line. Here's an illustration of that. Suppose we're looking at the curve y equals 4 minus x squared. We have three graphs of that curve here, at least part of the curve. This first graph is for values of x between 0 and 2. If you look at this horizontal axis, you can hopefully see a 0 here and a 2 here. What we're going to do is, right at x equals 1, let's zoom in on this curve to a small piece here. And that small piece will be still the curve y equals 4 minus x squared. But in this case, the x values are going to go from 0.7 to 1.3. It's still centered at x equals 1, which is right here. And so now we're looking at this part of the curve, and it looks pretty straight. But let's magnify it a little bit more so that we can hopefully see what's going on. So we'll take this piece of the curve that's inside this box, magnify it again, and we'll get a curve that looks like this. If we're just looking at values of x between 0.95 and 1.05, this is still centered at x equals 1. This curve that we see right here is the curve that we see right here, just magnified in this case. And as you can see, this looks quite straight. And so for all practical purposes, for computations, we could assume that this is straight and use properties of straight lines, for instance, in our computations. If it doesn't look quite straight enough yet, we could zoom in further and zoom in further and zoom in further until we get pieces that do look pretty straight. So basically, in the limit, as we look at smaller and smaller intervals of x centered at x equals 1, such as this one, and this one, the curve appears straighter and straighter and straighter. So let's look at the Biot Savart law in our discrete version. First of all, we're going to have Riemann sums around, and let's have Riemann sums with n terms. So we'll pick a value for n, the number of intervals in our Riemann sum, and theoretically at least, the larger n is, the better our approximation would be. However, with computers, larger n is not necessarily always better. We'll let theta sub k be 2 pi times k divided by n, the n that we had up here, for k between 0 and n. And then we're going to define our circle. The position function for our circle is going to be r sub c. R sub c of theta is going to be a, the radius of this circle, times the vector cosine theta, sine theta, 0. The z component here is 0 because we're assuming that this circular loop of current, maybe going through a wire, is embedded in the xy plane. We'll introduce this notation. Let r sub ck be r sub c of theta sub k. R sub c was up here. So if we look at this picture right here, r sub ck is the vector that goes from the origin of our three-dimensional rectangular coordinate system over to this point here for this kth little subinterval along this circle. We'll let delta L sub k be r sub c of theta sub k minus r sub c of theta sub k minus 1. This thing is a vector. It's the vector joining this point over to this one, starting point, ending point of this little arrow here, this vector. And we'll let r sub kp, p is going to stand for the point p that's up here, is going to be r sub p, which is the distance from the origin over to this point, minus r sub c of theta sub k. And when you do that subtraction, what you get is a vector going from this point right here out to the point P here. So what we're going to do is we're going to look at this little differential length here, I guess, which is actually a vector. And we're going to use that with the current going through it. This vector tells us the distance from the point P, and then we can apply the Biot Savart law to that to figure out what contribution the current in this little segment of the wire, let's say, what contribution does it give to the magnetic field out here. So let's look at the continuous version and over here, and the discrete version over here. Similarly, we'll have the equations for the continuous model here, the discrete model that we're going to be using in our computations down here. So in the Biot Savart law, we have a piece of straight wire, let's say, very small, infinitesimally small maybe, and it has a current I going through them. The length of this is going to be dl. Out here somewhere from this segment of wire, we have the point P, and the distance from that segment of wire to the point P is the vector r. We'll let the vector r hat be the unit vector in the same direction as r. In that case, we have dh equals I over 4 pi dl cross r hat over r squared. But since excuse me, r hat is equal to the norm r divided by the norm of r, if we plug this in to here, we can also rewrite it as I over 4 pi dl cross r, and then the norm of r cubed here instead of the norm of r squared that we have here. This difference in the denominators was because of the difference in the numerator, r hat here, r here. Now, if we go to the discrete case, we have this little line segment, which is actually part of our circular loop, very small. Let's call vector that goes along here, delta L sub k. Let's let the point from this line segment to P up here, let's let that be the vector R sub kp. So in that case, what we get instead of dH is we'll get delta H sub k, the contribution to H for this kth little piece of wire. At the point P up here is I over 4 pi delta I sub k cross R hat sub kp divided by R sub kp cubed. Now, in this picture, R hat sub kp is just the normalized version of R sub kp. Just as we did up here, we had R and R hat, sorry, and R here. We're doing the same sort of thing right here. And so this thing right here is going to be a contribution to the magnetic field at that point P. We're going to add up a lot of these little delta I sub k, delta L sub k, I should have said, going all the way around the circle to find the total contribution for all the parts to that magnetic field at P. So to just iterate what we did, we're going to partition that circular loop into n equal length arcs. And here's a picture of that circle in our problem of radius 2. And the circle is broken up into little arcs here. Then we're going to replace all those little circular arcs with corresponding vectors. And so now we have a picture that looks something like this. From here to here, we have a straight vector, which we call delta L1. The next one over is going to be delta L sub 2, and so forth. These are vectors. It doesn't look like this is quite bold, but over here we can see that L sub k is kind of bold. We keep going around that way, and let's say that the kth vector is right here. Call it delta L sub k. Delta L sub k is going to be a cosine theta sub k, a sine theta sub k, 0, minus a cosine theta sub k minus 1, a sine theta sub k minus 1, 0. So this gives us a vector starting at this point right here and ending at this point right here. We can do that for k goes from 1 to n, and it will give us all of these vectors going all the way around this circle. So then we can let delta H sub k of P be the contribution to the magnetic field at P attributed to the flow of current through just delta L sub k, this little portion right down here. And so delta H sub k of P is I over 4 pi times delta L sub k cross R sub kp over the norm or length of the vector R sub kp, that length cubed. In this picture, here is the vector going from the origin out to this point right here. That one we call R sub ck. The vector going from this point here, which is part of this region right in here, out to P, that's going to be R sub pk, kp, sorry, which appears right here in our formula. Let me reiterate what I just iterated. What we're going to do, remember, is divide the entire wire, that circular wire carrying the current, into n, actually lowercase n here, equally lengthed points, and replace those arcs with vectors. And we have a picture of something like this. We can see the circle here, these points. And when we have this kth sub interval giving us this kth little vector here, and the point P out here, we have R sub kp being the distance more or less from this infinitesimal interval here out to the point P. For delta L sub 1 and delta L sub 2, we would also have vectors leading out to this point P, and those would be R sub 1p, r sub 2p. The second index down here is just going to be p, referring to the point that these vectors point to the point p. Okay, and down here we have a reiteration of the formula for delta L sub k. This once again should be bold because this is a vector. Go boldly forward. And delta H sub k of p is the contribution of the magnetic field at p attributed to the flow of current through just this little piece of wire here, which on infinitesimal scales is essentially straight. So we now have a formula for delta H sub k of p, the contribution of one small piece of wire with the current running through it. We saw this several times already. So to find the total magnetic field at the point P due to that entire loop of wire with the current running through it, we would have to add up the contributions from each of those small pieces of wire. And so the total value of the vector H at the point P is approximately equal to this Riemann sum. Sum k goes from 1 to n, I over 4 pi, delta I sub k cross r sub kp divided by r sub kp in the norm cubed. And so what we then would have to do is for our particular values of the radius and the current and so forth, calculate this Riemann sum to get a hopefully good approximation of the magnetic field at one point P. Okay, so here's what's going to happen. We're going to use this formula for H of P over and over and over again at various points P out here in three-dimensional space. And for each of those points P that we choose in our three-dimensional space, we will draw a vector at that point representing this vector H of P. And that will give us a drawing of our vector field. So let's start to look at a Python program to create the vector field, create and display the vector field for this circular loop of current. First we have import numpy as np. What we do here is we import numpy library and we're going to use some of the functions in that library to create some mathematical constructs. We can use it for easily creating arrays and lists. And when we say as np, that means that later when we refer to that library numpy, we can use instead an abbreviation for it, np. np.linspace tells us that we're going to use a function called linspace that comes from numpy, which we abbreviated as np since that's the way we imported it up here. Okay, if we look at this next line, import matplotlib.pyplot as plt, what does that do? It imports the pyplot module from the matplotlib library, which will help us to create plots and axes within those plots and some other functions which can alter these plots, some plotting functions. And we'll see those used later, but not quite in this little bit of code here. If we look at x equals np.linspace minus 5, 5, 6, what that does is it creates a list of 6 equally spaced numbers, starting at minus 5 and ending at 5. And we're going to store that sort of list in X. We're going to store it also in Y and a list with similar numbers in it for Z. Okay, coming down here, we're going to set A equals 2. Our program is going to use a circular piece of wire with radius 2, and here we're just setting A equal to 2, which we'll use as the radius later. When we come down here, we have positions equals an empty list and fields equals an empty list. So we created two empty lists here. What will happen later is we'll fill up the list positions with the starting points of quivers, arrows basically, and the fields list is going to have the directions of each quiver. So what's going to happen is these will be multi-dimensional, and the fields is actually mathematically going to tell us what the vectors are, but they're going to be starting at certain points in space, and the points in space where these arrows or quivers start are going to be in this list positions. Let's look at this second portion of code. Let's remember that capital X, capital Y, and capital Z were created using linspace from -5 to 5, comma 6. So when we have these nested for loops here, for little x equals x, for little y equals capital Y, for little z equals capital Z, what we're going to do in iterating through these nested for loops is create lots of points x, y, z, which we can think of as a point in space, three-dimensional space, whose coordinates are somewhere between -5 and 5. So after we set up a value for x, y, and z in this big loop, we'll let RP excuse me, be the array having the values x, y, and z in that array. So basically this is going to point to some point out in space, which we can think of as a point P. And we're going to have to store these somewhere so that later we can start displaying this stuff, and also for calculational purposes. So for each point in that three-dimensional space, we have a vector RP pointing to that point. We're going to have to form a Riemann sum involving the kth little component of the current. And to do that, we saw in our calculations previously, we defined something called R sub pk, and that was the distance from the kth chunk to R sub p, RP. And so that's basically what we're doing here. R high and R low are defined up here, and those are basically going to give us stuff that involves the endpoints of that little interval I sub k. And then the code in here is very similar to the calculations we showed previously, and what we're doing in that code is adding the terms to form the Riemann sum, which will give us the vector field at one point P, which is referred to in this program by the vector RP. Once we have that vector specified by its initial position and the direction which it's going, we will append those to the position and fields arrays that we had earlier, which started as empty, and now in this big loop we're filling them up. And now let's consider the last part of this program. These first two lines here we've already seen, so let's come down to here. We have AX dot quiver positions I0, positions I1, or :0, :1, positions :2, fields :0, :1, :2, what this part does is gives us the starting point of the arrow in terms of the positions array elements, and the vector itself, its direction and magnitude, are basically given by these fields, sub 0, 1, and 2. We have colons here because we're loading a multidimensional array basically in here, and we're referring to colon means basically all of the possible subscripts or indices that you can put in here. So anyhow, we have that quiver statement, and we're going to let the length be 1.0, and normalize being true says that we're going to let all of the vectors have the same length. We could have normalize equals false here, and in our final rendering of the vector field, you'll see that some arrows are extremely short, others could be quite long. So in this part here, we're defining the family of quivers that we want to display, and we have two multidimensional arrays, positions and fields, that tell us where the quivers or arrows start, the vectors start, and what direction they're going to be pointing in. Okay, so let's look at the next part of this code. Here, when we look at this, we're going to be defining the circle of radius 2, a equals 2 in our case, in the xy plane, and we're going to put later in the code a statement to plot that particular circle, and we want the circle to be in red. So let's take a look at this for a second. This basically is just the parametric equations for a circle. We'll let theta equal np dot linspace, and we'll go from 0 to 2 pi with 100 points being given in the interval from 0 to 2 pi, equally spaced points. And then x will be 2 times the sine of theta. Y will be 2 times, I should have said cosine theta here. X equals 2 times cosine theta. Y equals 2 times sine theta. And z is just going to be, in our case, 0. Since our points are in the xy plane, the z-coordinate of all of the points on that circular loop, the z-coordinates are going to be 0. So this is code that's going to define our circle. And then down here, this line, we have the code for plotting that circle. ax.plot, and we have x, y, and z here. So we're going to plot x, y, and z. The color of that circle is going to be red. The line width will be 2, so it's just a little thicker so we can see it more easily. And then, after we do that, we're going to finish up by specifying the numbers on each axis and the labels on each axis. So ax dot set x lim goes from -5 to 5. Similarly, we set the numbers on the y-axis going from -5 to 5. Notice we have y lim here. And for the z limits, -5 to 5. And on the x-axis, we'll use a label of x. On the y-axis, we'll use a label of y. On the z-axis, we'll label that with a z. And we'll also put a title on our three-dimensional drawing using ax.setTitle, and the title magnetic fields from circular current loop. And then after all of this is done to set up our three-dimensional drawing, our three-dimensional plot, we'll follow it at the end by plt.show with parentheses here. PLT, remember, was the pyplot module that is in the library matplotlib. And so this is actually the one that's going to be doing the drawing on the screen of our three-dimensional axes X, Y, and Z axes, plus all the quivers that we generated up here with this MV quivers. So after all of this is executed, we will have our three-dimensional rendition of the vector field, and it is interactive. Once you have that output in a figure, we can rotate it around to look at it from various angles. So we are now looking at Spider in interactive development environment, and this is the program that we have been looking at for the last few minutes. We can get it to scroll and we can see the whole program is here as described, and we're going to run this program. So I'm going to go up to a run command, which you can't see, and run this, and what happens is we get a field, a vector field in this figure. If we click on this with the left mouse key and move the mouse, we see that we can look at this from various angles, above and below, for instance, and to the left and to the right. And if we look at this kind of carefully right here, we can see maybe how the field kind of runs loops around the coil, this red coil, this circular loop that is. And if we think about it for a while, we can imagine what the flow lines will look like for this field. Very similar to what you find in textbooks. I'd like to thank you for watching this video. In this video, we rendered the H field for a circular loop of current. Along the way, we introduced the Biot Savart law. We saw how to compute the H field at a selected point out in space, and we used these ideas to compose a Python program that would display the H field. Thank you again for watching, and have a good day.